Hi students, Miss Gardner here, and I am going to take you through our Unit 3 notes, Part 2, where we're going to talk about isotopes and average atomic mass. So make sure you have your notes document out and you are ready to fill in the missing portions and any questions as we go through this lesson. Okay, let's look at these three different versions of carbon atoms shown here. These are Bohr models. Now, we all know they're carbon because they each have 6 protons. All right, the number of protons tells me the identity of the atom. These each have 6, so they're all carbon. Okay, so number of protons stays the same between each of them. What else is similar? They all have the same number of electrons. They all have 6 electrons. So that means they're also all neutral. Okay, now what is different between each of these? You can look at the nuclide symbols that are down below here. We have one that has a mass of 12, one that has a mass of 13, and one that has a mass of 14. Okay, so they each have a different mass. Now, how do they have a different mass? That's because they all have different numbers of neutrons. In carbon 12, we have 6 neutrons. Carbon 13, there are 7 neutrons. And carbon 14, there are 8 neutrons, leading to these different masses. Okay, so these different versions of carbon, these are actually different isotopes of carbon. So let's look at now some different versions or isotopes of hydrogen. All right, we have one here. This is regular, well, what we'll refer to as regular hydrogen. That's also called protium. It has 1 proton and 1 electron. So we have a mass of 1. Now, we can have an isotope of hydrogen that has 1 proton and 1 neutron. 1 proton and 1 neutron, 1 electron. This is called heavy hydrogen. It's also called deuterium. The nuclide symbol for that, it has now a mass of 2. All right, we can also have a third isotope called hydrogen 3, also called tritium. This has 2 neutrons, 1 proton, 1 electron. All right, so this is a mass of 3, but they all have the same atomic number. Okay, so looking at these three, which version or which isotope of hydrogen do you think is the most commonly found in the universe? How would we know that? Well, let's look at the periodic table. Look at this symbol here of our periodic table and the average atomic mass. The average atomic mass is 1.01. So that tells me that when I average all of these different isotopes in the entire universe, most of them have a mass of about 1. So I expect the most abundant isotope, or most common, to be hydrogen 1, or protium. Okay, so we can figure that out from our average atomic mass. We'll learn later in this lesson how to calculate that. Isotopes are versions of an element that vary in their number of neutrons. Now, why do isotopes even exist? Well, it's just because when all the elements were first created in the universe, starting out with hydrogen and helium from the Big Bang, and then later in different aspects of fusion in really hot stars when all our other elements were created, there was a distribution of the types of atoms that were produced. So yes, most hydrogen atoms that were produced have 1 proton and 1 electron, but nature isn't perfect. So there are some that also have 1 proton, 1 neutron, and 1 electron, some that have 2 neutrons. All right, and then so this distribution of isotopes is actually super useful in things like carbon dating. If you've ever heard of carbon dating, that's how we can figure out relatively accurately how old a fossil is by measuring the amount of a certain isotope of carbon that is still present in there. We use isotopes to treat different types of thyroid cancer. We use isotopes to do medical imaging. If you've ever gotten like a CT scan, you drink something that has an isotope of barium in it. Of course, isotopes are used in nuclear reactions where we have nuclear chemistry. You've probably heard of radioactive isotopes, and you might think of those as being dangerous. Some of them certainly can be, but some of them can also be very useful. So let's talk about a little bit more. Isotopes, how do we name them, and how do we calculate their relative abundance? Okay, so from our nuclide symbols, we can actually figure out a whole lot of information. So just a reminder, in our nuclide symbol, we have our mass number up top and our atomic number down below. Okay, so let's fill in our charts for these isotopes. All right, so we have a isotope here of potassium. Its atomic number, 19. Mass number, now I put an asterisk here. Now this is not the mass from the periodic table. Notice I'm just asking what is the mass of this specific isotope. So we're talking about one specific atom. On the periodic table, that mass, that is an average. Okay, so the mass number here is 40. Number of protons, same as our atomic number. And to figure out neutrons, we'll just take our mass minus protons to get neutrons. So that would be 21. Okay, let's do the same thing for this isotope of fluorine. Atomic number is 9. The mass number, 18. Protons, same thing as atomic number, that's 9. And neutrons, we calculate, we'll do mass minus protons, we get 9. All right, so here let's look at this isotope of this element W. It is tungsten. It has an atomic number of 74, mass number of 180. 74 is also the number of protons. To get neutrons, we'll just do 180 minus 74. This isotope has 106 neutrons. All right, so you'll notice as you get down to heavier and heavier elements on the periodic table, there's a bigger difference between the amount of protons and neutrons there. And that's just because there's a lot of positive charges in the nucleus, and those neutrons seem to be there to stabilize it. Okay, so naming an isotope. So we can, there's a convention for naming this, and it's very straightforward. So you just name the element, and then you list the mass number after the element's name. All right, so for example, a nitrogen atom that has a mass of 15 is called nitrogen 15. Okay, pretty straightforward. So let's go ahead and name these isotopes. All right, you might want to have your periodic table handy so you can see the name of each element. All right, so find element with a symbol B, and then we're going to put the mass number behind it. So this will be boron 11. All right, so next one here we have element I, that's iodine. The mass number is 131. Here we have U, uranium, mass number 238. O, that is oxygen. The mass number is 17. Oxygen 17. Okay, so we have mentioned average atomic mass a whole lot and talking about like that's a decimal because it's an average. Well, what is it an average of? It's actually an average of the masses of all the isotopes of that particular element. So if we look at a sample of magnesium, like those little strips that we burned in class, and some of you in my class, you got to mess around with them a little bit to feel their texture. So if we zoomed in on the atomic scale and looked at the individual atoms there and took a sample, we would see mostly magnesium 24. This is our zoomed in picture here, right? Magnesium 24, 24, 24, but a few magnesium 26s and a few magnesium 25s. Okay, so this is our zoomed in view. If you look there, how many different isotopes do you see? I see magnesium 24, 25, and 26. All right, so there are 3 different isotopes of magnesium. Now, I'm going to let you do this practice here. List the names of them. I've given you the example for magnesium 24. List the other 2. Okay, now, this is just a tiny sample, but it is representative of the entire amount of magnesium in the universe. So this is 20 atoms. If you counted this, so you'd see there's 20 different magnesium atoms here. Now, let's extrapolate or expand that data set from there to make some predictions about what we expect to find in a sample of 100 magnesium atoms. Okay, so looking on this, 2 out of my 20 are magnesium 26, right? There's one here and there's one here. So 2 out of 20 is 10%. All right, 2 out of 20 are also magnesium 25. So there's one here and one here. So that's another 10%. The remainder, 16 out of 20, are magnesium 24, so that's 80%. So if I had a random sample of 100 magnesium atoms, I'd expect 10 to be magnesium 26, 10 to be magnesium 25, and 80 to be magnesium 24. All right, so what is the most abundant of this, the majority? Well, magnesium 24, that is my most abundant isotope. Okay, so let's calculate average atomic mass, and I think this will be helpful for you in understanding your grades as well. The average atomic mass is just the sum of all masses of a known isotope of an element multiplied by their respective natural abundance. This is a weighted average. This is exactly how your grade is calculated at Riverside or Heron. So let's figure out why, if you do poorly on a mastery score, why does it tank your grade so easily? Okay, here's our example. So let's say you have 100% on your practice. You do all your IP, you've got everything turned in. But you didn't study for a recent test and you got a 65 for your mastery score and your grade dropped like crazy. You're like, what? My other score is 100. Why doesn't that matter? Well, because we weight our grades. 30% is practice and 70% is mastery. So the way your grade is calculated is we take that grade of 100, we multiply it by 30%, then we add that to your grade of 65, multiplied by its weight, or 70%, all right? Then that divided by 100 gives you a grade of 75.5. Okay, so notice here, even if you have 100% on all your homework, a low mastery score can really affect your grade. Okay, so here also when I'm doing the math, if you prefer to just convert 30% to 0.3 instead of dividing by 100, that's also fine. That is just a shortcut way. Okay, so let's apply this to average atomic mass. It's the exact same principle. So the average atomic mass takes the mass of your first isotope multiplied by its relative abundance, plus the mass of the second, times its relative abundance, plus the mass of the third, and so on and so forth. There are some elements that have, I don't know, like more than 10 different isotopes out there. Most of them have maybe between 2 and 5. We'll just look at ones that have a maximum of 3. All right, then those you'll just all divide by 100 to get your average atomic mass. Okay, so let's do a practice for hydrogen. Hydrogen 1 has an average abundance of 99.985%. Hydrogen 2, average abundance of 0.015%. All right, so let's calculate the average atomic mass. Okay, so we will take the mass of the first one, 1, right? It's hydrogen 1, multiplied by its relative abundance. We'll add that to the mass of the second isotope, hydrogen 2, multiplied by its percent. All right, then all that will be divided by 100. Go ahead, put this in your calculator. Make sure you use appropriate parentheses. And you should get 1.00015 as our average atomic mass. All right, you'll notice this is pretty close to what's on our periodic table. We are rounding the masses of protons and neutrons here, but this is our average atomic mass. All right, I'm going to do one more practice with you, and the third one you'll do on your own. All right, average atomic mass of oxygen. We have 3 isotopes this time. Oxygen 16, 17, and 18. All right, oops, that should be oxygen there. Okay, so oxygen 16 has a mass of 16. It has a relative abundance of 99.76. So 99.76% of all the oxygen out there in the universe is oxygen 16. All right, oxygen 17, mass of 17 times 0.04%, then plus our third isotope, oxygen 18 times 0.20%. All right, so we'll sum all of those products together, divide by 100, and we should get 16.0044. Okay, let's ask, does that make sense? Does it make sense that the average atomic mass is closer to 16 than 17 or 18? Yeah, almost 100% of the isotopes out there are oxygen 16. Okay, so that makes sense to us, and that is our weighted average. Okay, so do that third problem on your own, and now you are able to define what an isotope is, determine your number of neutrons from a nuclide symbol, name isotopes, you can explain what relative abundance is, and you now know how to calculate the average atomic mass given the relative abundance. So now you know why all those masses on the periodic table are decimals. All right, rewatch this video if you missed anything, and reach out to your teacher with questions.